10 billion fishing hooks are manufactured in industrial facilities across the globe every single year. Behind this immense volume lies a production infrastructure that operates with calculated, high-speed mechanical precision. Why is such a massive scale necessary for a tool that appears so basic? The global fishing tackle industry is valued at over $15 billion, and this small metal component remains its most consumed and essential element. Without these few grams of shaped steel, both massive commercial fleets and solo recreational anglers would be unable to secure a single catch. One can notice the remarkable load-bearing capacity hidden within such a small frame. It only looks obvious that a piece of wire should hold a fish, but in reality, a high-quality hook must withstand between 300 and 500 pounds of pulling force. This resistance is roughly equivalent to the weight of a small piano, a strength-to-weight ratio typically reserved for advanced aerospace or structural engineering components. But this is just the beginning. The life of a hook starts as a massive coil of high-carbon steel compressed into heavy, tight loops. This raw material is mounted onto a rotating payoff reel that gradually feeds the metal into the start of the production line. Because the steel retains a natural curvature from its time spent wound in the coil, it must immediately undergo a correction process. It passes through a wire straightening machine where a series of offset rollers apply continuous, minute pressure to the surface. The equipment gradually removes every trace of the curve, forcing the wire into a stable linear form without distorting the integrity of its cross-section. Once the metal is perfectly aligned, a driven feed system takes over to maintain a constant delivery speed. Transition to the next level. At the end of this stage, the wire enters an automatic cutting unit where blades divide the strand into segments. Depending on the specific requirements of the hook size, each segment is cut to a length between 1 and 3 inches. The entire mechanical sequence runs at a blistering pace, with feeding systems processing hundreds of feet of steel every 60 seconds. Machine configurations allow for the output of several hundred to more than 1,000 individual segments in a single minute. It is visible how the straight steel pieces slide down a metal chute the moment the blade closes, dropping into a circular collection tray. When the accumulation reaches a specific volume, workers move the standardized segments into longer containers for transport. From these uniform pieces of steel, the material transitions into the critical point forming stage. Each blank is fed into a high-speed grinding machine where a rapidly rotating abrasive wheel waits to define the edge. The process is only gaining momentum. The tip of every steel segment is pressed with light, consistent pressure against the velocity of the spinning wheel. Extremely thin layers of carbon steel are shaved away to create a smooth, tapered point that is sharp to the touch. One can notice how tiny sparks scatter at every moment of contact, signaling the friction required to separate material from the core. Technical sensors must monitor the duration of this contact to prevent the metal from overheating and losing its structural properties. At first glance, the sharpening seems like the final step, but in reality, the sharpened blanks must now enter an automatic forming machine. Each piece moves through a precision channel where it is briefly secured against a steel die to prevent any shifting under load. The first operation within this die is end pressing, a process where high pressure flattens the tail of the segment. This expansion of the metal's cross-section provides the necessary surface area for the formation of the eye where a fishing line will be attached. The pointed end then passes beneath a micro-stamping blade to create the barb, a feature designed to prevent a catch from escaping. The entire sequence is executed in a cycle lasting less than 1 second. Everything only gets more complicated as the final shape is struck into the steel, but the mechanical die opens with the hiss of its release. The newly formed hook slides cleanly off the platform and drops into the waiting collection tray below. Thus ends the initial shaping phase of the production cycle. 1,400 to 1,600 degrees Fahrenheit is the intense thermal range the hardening furnace reaches to initiate the transformation of the steel. Why must the unfinished hooks undergo such extreme heating immediately after forming? At first glance, the shaped metal appears ready for use, but its internal structure remains too soft to withstand the mechanical stresses of a strike. The heating process allows the internal crystal lattice of the material to reorganize at a microscopic level, creating a state that can be permanently altered. But this is just the beginning. The hooks move along a metal conveyor belt that feeds them through the continuous hardening furnace with a steady mechanical rhythm. One can notice how the dark metal begins to glow as the temperature climbs toward the target threshold. Almost immediately after reaching the peak heat, the components are plunged into a controlled cooling environment for rapid quenching. This sudden drop in temperature effectively locks the transformed crystal structure into place, resulting in a dramatic increase in the hardness of the metal. Hardness alone, however, creates a significant technical disadvantage. edge. It only looks obvious that a hard hook is a better hook, but in reality, steel that has been quenched to maximum hardness becomes excessively brittle and prone to sudden fractures under tension. Therefore, the production cycle transitions to the next level, which is tempering. During this stage, the hooks are reheated to a significantly lower temperature than in the first furnace. This secondary thermal cycle does not increase hardness. Instead, it relieves the internal stresses within the steel and restores a measured degree of toughness. The process is only gaining momentum as the hooks emerge from the tempering furnace. Residual oils and surface contaminants from the thermal baths are quickly stripped away to prepare the metal for chemical processing. The equipment gradually moves the parts into the surface finishing stage, which starts with a precise acid treatment. A controlled chemical solution dissolves oxide layers and any lingering impurities that might interfere with the integrity of the coating. One can notice how the surface of the metal becomes chemically active once the outer film is removed. This activation ensures that the subsequent protective layers bond tightly to the steel substrate rather than merely resting on the surface. Everything only gets more complicated as the hooks enter the electroplating bath. Within these tanks, an electrical current is utilized to deposit a thin, uniform protective layer of metal onto the steel hooks. Depending on the specific requirements of the final product, the coating might consist of nickel, black nickel, or tin. This metallic barrier serves as a permanent shield that limits direct exposure to water and oxygen, preventing the onset of corrosion. In a real manufacturing environment, this immersion sequence is a repetitive and highly structured operation. The hooks do not simply visit one tank. They pass through an array of containers arranged in a sequence of acid, rinse, plate, and rinse. Sometimes the cycle repeats through additional rinsing stages to ensure that absolutely no chemical residue remains trapped in the bends or barbs. It is visible how the components are lifted and lowered by automated systems between the various chemical baths. Once the chemical treatments are finalized, the hooks are moved into a dedicated washing and drying zone. High-pressure jets of clean water flush away any remaining traces of the plating solution, while streams of heated air rapidly evaporate all moisture. This speed is critical to prevent flash oxidation, which can occur within seconds on a damp metal surface. At this point, the metal surfaces appear brighter and more stable, indicating they are fully prepared for the final stages of the production line. 15% of each batch, or a similarly strictly defined representative sample, must undergo rigorous mechanical validation before leaving the facility. The hooks first pass through a high-resolution vision inspection system that scans for geometric deviations. Alongside this visual check, samples are placed into a tensile testing machine where force is gradually increased to the design threshold. This test confirms that the hooks will neither straighten out nor fracture when subjected to a heavy load. The process is only gaining momentum as random checks are also performed on point sharpness and the exact positioning of the barb. Once the quality control systems provide approval, the hooks are routed to the automated counting stations. The equipment separates the parts into preset quantities and slides them into their primary protective packaging with mechanical precision. Labels are applied and the units are sorted by product code before being packed into large shipping cartons. The camera glides along the final conveyor as the boxes are sealed for global distribution. From here, the finished products move toward the loading docks, completing their transformation from raw wire to specialized tools. The metal leaves the final station, transitioning into a calm stage as it enters the logistics network. Thus, the production cycle concludes, having turned a simple alloy into a high-performance component through a sequence of thermal and chemical mastery. 150 grams of carbon fiber can conceal a complex engineering system within the structure of a single fishing rod. Why is this slender backbone of the fishing setup considered a marvel of modern material science? It would seem a simple tapered pole could be fashioned from any flexible material, but the requirements for modern angling demand extreme strength to weight ratios. The answer lies in the precise composition of carbon fiber and fiberglass pre-impregnated with heat-reactive resins. These specialized fibers are already saturated with a chemical binding agent designed to harden only when exposed to specific high temperatures. But this is just the beginning. If the resin remains at normal ambient room conditions for an extended period, it begins to cure prematurely, rendering the expensive material into useless waste. Because of this extreme chemical sensitivity, all raw materials are stored in specialized cold rooms at temperatures below 32 degrees Fahrenheit and are only removed at the exact moment they are required for the production line. One can notice how the clock begins ticking the second the material leaves the cold storage unit. The technicians unroll the sheets and lay them perfectly flat onto the cutting table, adhering strictly to every technical outline provided by the engineering department. A technician measures the alignment by hand, carefully squaring the edges of the material before the machine executes each pre-programmed cutting pattern with controlled mechanical precision. Each individual cutting cycle can process between 8 and 10 layers of carbon at the same time to maintain high factory productivity. Accuracy must be preserved down to tiny fractions of an inch during this phase. It is visible how the carbon is rarely cut in straight lines, as the machine instead produces triangular forms or complex diagonal patterns. This specific cutting geometry determines exactly how force travels along the length of the rod when it bends under a heavy load. A single piece cut off by even a fraction of an inch can shift the entire flex point of the rod, ruining its intended action. Everything only gets more complicated as the transition to the forming stage begins. The material must be positioned with absolute precision onto the mandrel, which is a long stainless steel shaft serving as the internal forming mold. This steel core is typically treated with a non-stick release agent so that after the heating process, the finished blank can be separated cleanly and without any structural damage. Once the adhesive is applied evenly along the steel shaft, the technician uses a small heated iron or a localized heating tool to hot tack the first layer of carbon into its starting position. Each carbon piece is aligned carefully along the center line of the mandrel and squared at both the tip and the butt ends before being secured. If the first layer is off-center by even a millimeter, the entire rod blank that follows will inherit that misalignment through every subsequent layer. At first glance, this looks like a job for automation, but in reality, there are no robots or laser guides involved at this critical stage. Everything depends entirely on the trained eye and the tactile experience of the technician. The rod truly begins to take its physical shape the moment the mandrel is placed onto the rolling table. The machine rotates at a slow and controlled speed, while each layer of carbon fiber is wrapped around the steel core under the total command of the craftsman. From the rotation speed and the applied hand pressure to the precise stopping points, every movement is calculated at the exact instant the next layer is laid down. As the core turns, the fiber layers tighten against one another with increasing tension. The material edges move closer together, and the rod gradually lengthens and tapers following a geometry that has been mathematically calculated. After the primary layers are complete, the technician adds reinforcement layers at high stress zones, specifically near the handle area. These reinforcements are not applied simply to make the rod thicker, but to fine-tune the sensory feedback during casting or while fighting a fish. The process is only gaining momentum as the structure nears its final preparation. Once all the carbon fiber layers and the reinforcement plies have been fully wrapped, the rod blank moves into the stage of heat-resistant tape wrapping. The facility utilizes nylon tape, cellophane tape, or specialized vinyl tape to tightly bind the entire length of the blank before the thermal processing begins. The mandrel is mounted onto a specialized wrapping machine where it rotates steadily as the tape is applied in a continuous overlapping spiral. One can notice the consistent pressure applied from one end to the other as the tape locks the shape of the rod in place. The purpose of this step is to keep every internal carbon layer pressed firmly together throughout the intense heating cycle that follows. As the tape tightens, the material beneath is compressed with total uniformity, creating a consistent wall thickness along the entire length of the blank. At this stage, the mandrel serves as the internal mold, while the tightly wound tape functions as the external mold, holding the structure stable. The material is now fully prepared to undergo the curing process, where the resin will finally reach its maximum hardness. From here, the transformation moves to the next phase of processing without haste. 284 degrees Fahrenheit is the standard temperature required to initiate the thermal transformation within the curing oven. Why is this specific heating cycle monitored so stringently by computer systems? A simple increase in heat would seem sufficient to harden the material, but without a perfectly even rise in temperature, the resin would cure at different rates, creating internal stress points that would inevitably lead to structural failure under tension. The process is only gaining momentum as the mandrels, wrapped in heat-resistant tape and carrying the raw rod blanks, are hung onto racks and moved into the chamber. This curing phase typically lasts for 2 hours, providing the necessary window for the heat-reactive resin to transition into a liquid state. One can notice how the resin begins to flow between the carbon fiber layers, saturating the fabric and bonding the separate wraps into a single unified structure. What were originally independent sheets of carbon now merge into a nearly monolithic rod blank. At first glance, the assembly remains malleable, but this is a temporary state. Before the thermal cycle concludes, the blank can still be removed or adjusted if a technician identifies a misalignment. It gets more complex further on. Once the chemical reaction is complete, every physical deviation and every microscopic shift in the fibers becomes permanently locked into the internal matrix of the rod. Therefore, factories enforce absolute control over the stability of the oven environment to prevent even a single degree of fluctuation. The heating cycle ends, and as the material begins its initial cooling phase, the mandrel extraction stage begins. The equipment gradually transitions the blank to a dedicated separation machine. Here, a holding mechanism clamps the internal metal mandrel firmly in place, while a pneumatic pulling arm prepares to apply force. The arm draws the core out of the rod with a steady, powerful motion that must overcome the significant friction generated during the curing process. Everything only gets more complicated if the heating was inconsistent. The pulling force must remain smooth and precisely calibrated to ensure the carbon structure does not deform while it is still settling. It is visible how the mandrel slides out cleanly if the resin bonded correctly, leaving behind a perfectly hollow and straight rod blank. Any difficulty during this extraction serves as an immediate indicator of a surface defect or a thermal error. A technician performs a rapid inspection of the blank's straightness using only trained eyesight and tactile feedback. This reliance on experience allows for the detection of subtle ripples that sensors might overlook. The process does not end at this stage. Once the blank has reached room temperature, the removal of the outer wrapping tape begins. The technician peels the tape away by following the original spiral direction, moving continuously from the tip toward the butt of the rod. As the protective layer is stripped, the blank is revealed with a series of spiral marks and ridges formed by the compression process. These rough surface features are the physical imprint of the pressure applied during the bake. Transition to the next level. The blank moves to the cutting station to achieve its final length and shaping. The technician places the rod onto a specialized support fixture and aligns it with precision along its central axis before feeding it into the blade. The cutting disc rotates at a high, steady speed, removing excess carbon material from both ends to bring the blank to its exact architectural standard. Once these dimensions are locked, the component enters the grinding and sanding stage. Dry sanding serves as the first corrective measure, breaking down the larger ridges and smoothing the sharp edges left by the tape. The technician rotates the rod by hand with a constant motion to ensure the abrasion is uniform across the entire circumference. But this is just the beginning of the refinement. After the initial pass, the blank undergoes wet sanding. Water flows over the surface to reduce friction and carry away fine resin dust, allowing for much finer control over the sanding pressure. The rod sections move to the joint fitting area for a critical alignment inspection. The technician inserts the tip section into the butt section, gently twisting the assembly to test the integrity of the connection. A joint that meets the required specification must engage evenly with no perceptible play or sound when moved. It only looks obvious to the untrained eye, but in reality, a deviation of just 0.04 of an inch can disrupt the entire continuity of force transfer through the rod. The check is vital for the performance of the final product. Once the fit is approved by the technician, the sections are separated once again. They are grouped into bundles based on their specific model and length, secured neatly to prevent surface damage. The material leaves this stage of production, transitioning into a calm stage as the bundles are sent to the painting workshop for the final aesthetic finish. 100% of the surface preparation is now finished, and the rod blank transitions immediately into the specialized paint shop. The component is secured onto a precision rotating machine that maintains a constant speed to ensure the coating applies evenly across the entire 360-degree circumference. Why is the initial application of a white base coat or primer so critical for the rod? This layer serves to unify the composite surface and provides a neutral foundation that significantly enhances the color vibrancy of every subsequent layer. Once this base coat has dried completely, the blank receives its primary color coating. Fluorescent paints are most frequently utilized at this stage to maximize visibility during outdoor use, particularly in low light conditions or over the water. It gets more complex further on. Depending on the specific order, the rod may also undergo customization to meet individual customer requirements. At first glance, the painting looks complete after the color is applied, but in reality, the structure requires a protective shield. The process concludes with the application of a clear urethane top coat. One can notice how the equipment sprays or wipes the liquid on in an even film to create a smooth finish that resists physical scratches, ultraviolet exposure, and saltwater moisture. The rod moves into a dedicated drying room. This allows the protective coating to cure and stabilize fully before the product transitions to the next stage of the assembly line. Once the painting process is finalized, the rod blank is transferred directly to the handle assembly area. Here, all handle components are installed entirely by hand without the use of automated presses. The technician applies a measured layer of adhesive along along the blank and then carefully slides each handle section into its designated position according to the engineering design. Depending on the specific model being produced, handle materials may consist of Avafoam, natural cork tape, or specialized heat shrink tubing. Next comes the critical installation of the reel seat, which is the specific component responsible for securing the fishing reel to the rod. Alignment must be executed perfectly along the central axis of the rod. Why is such jewelry-like precision required for a simple seat? Even a slight misalignment of a few millimeters can create hand discomfort and negatively alter the feel of the rod when it is under a heavy load. Once the reel seat is fixed permanently in place, the butt end of the rod is finished with either a reinforced butt cap or a gimbal. At this stage, the blank is no longer just a smooth composite tube. It begins to take on the specific shape, balance, and tactile character of a finished fishing tool. Guide installation begins immediately after the handle is secured. First, the technician marks each individual guide position along the entire length of the rod according to the layout. These marks determine exactly how the fishing line will travel and how the load will be distributed along the carbon structure during active use. Each guide is placed onto its marked position and aligned by eye along the central axis. Everything only gets more complicated. Once the position is verified as correct, the technician begins wrapping high-strength thread around the guide foot. One hand holds the guide steady while the other wraps the thread evenly and tightly to secure it to the blank. It is visible how every wrap sits cleanly beside the next with no gaps or overlaps allowed in the weave. After all guides are wrapped, the technician performs a final visual check along the entire guide line. This confirms the straightness and balance before the rod moves on to the finishing coat stage. After the guides are secured with thread, the rod enters the epoxy coating stage. The technician uses a fine brush to apply a base layer of epoxy over each wrap, ensuring the resin penetrates fully into the thread fibers. Once the base coat reaches the proper level, the rod is placed onto a rotating rack or a turning drum. This rotation allows the epoxy to level itself evenly around each guide using centrifugal force and gravity. Next, the rods are passed through a hot airflow or an ultraviolet curing chamber. Heat and ultraviolet exposure partially cure the epoxy, stabilizing the wraps before the next layer is applied. A final epoxy coat is brushed on to create a thicker, glossy, and durable surface. In a single day, the factory consumes a very large volume of finishing material during this specific stage. Each drying rack can hold dozens of rods at once, rotating continuously to ensure the epoxy cures without sagging. The process is only gaining momentum. The tip section and the butt section of the rod are joined together for the first time. The technician inserts the tip into the butt in the correct orientation and applies a gentle twist to check the fit. The connection must engage evenly, being neither loose nor excessively tight, and must slide smoothly throughout the entire insertion range. Once the two sections are fully seated, the rod is placed on the inspection table to check axial straightness. One can notice how the technician rotates the rod slowly, observing with the naked eye and feeling by hand to confirm the axis remains true. The rod is then flex tested under a controlled load to verify overall strength and structural stability along its entire length. Finally, the entire rod is wiped down to remove fingerprints, dust, and any excess adhesive residue. The surface is examined one last time under strong lighting to detect scratches or minor imperfections. When all criteria are met, the rod is tagged, placed into a protective sleeve, and packaged for shipping. Thus, the steel and composite components reach the standard ready for the final journey to the consumer.